non-Lagrangian. If it's gravitationally anomalous, there is no lattice regulator. And the obstruction to factorization can be thought of as a kind of quantum information theoretic refinement of the Nielsen-Ninimian theorem, establishing a parallel no-go theorem for tensor factorizations. Boundary conditions play an important intermediate role, and we've needed to assume Friedan and Konechny's hypothesis to make the proofs work. There may be some way of circumventing that. I hope there is, but maybe it's fundamental. I don't know. The obstruction to factorization is physical, not merely formal. States with vanishing correlation between regions of space do not appear to exist, for instance, in chiral fermion theories. So, thank you.
These earlier papers.
Which other papers?
In particular, the paper by Wall and Iqbal.
Huh.
Sorry. No, but I'm actually, because this is a point that I think they already made.
They knew that there was something they had to inoculate themselves against, but the inoculations don't work.
I mean, it seems to me that they have some formula that says, here's you choose some. So they already point out that the entanglement entropy depends on how you slice the causal diamond, and then they write out some formula for how it transforms anomalously under diffeomorphism. So what is right?
What?
No, so isn't this a point that they have already made, and including saying something about how it transforms under diffeomorphism?
No, because there's no it.
Well, if you add some additional information, you could probably, if you give me some slicing, or you give me.
That's the point. You might think so, but there's no notion of entanglement in these theories that makes sense. It's not given some slicing. Okay, I give you a slicing. You try to define some tensor factorization with Hilbert space. You can't. There is no such factorization within Hilbert space. If there were, there would exist states, for instance. So, okay, if you believe that there exists such a factorization, you send me, you can email me tonight, or even tomorrow morning. Email me a state with vanishing correlations between the two sides. I don't care whether it's Lorentz invariant or not, whether it's covariant under how you slice. Just slice any way you like. Slice the slice into two parts. And then find me a factorized state.
If you go beyond Napa-Cloud, would you not have a favorization? It's a magnetic theory.
Sorry?
I said, if you beyond locality, would you not have a favorization from the magnetic theory?
You see, if you don't assume locality.
Yeah, because if you assume locality, we use volume H bar to describe your Fourier space.
No. The locality is the whole point. I mean, in other words, in Fourier space, for instance, obviously the theory tensor factorizes into an infinite tensor product of Fock modes. But that's not the same thing as saying that tensor factorizes in a way that local operators in A act in one factor and local operators in B act in the other factor. Right? So locality is part of what we mean by saying that there exists or doesn't exist a tensor factorization. No, right, so these papers, so...
But it may depend on how you regulate the K, which is...
No, sir, it does not. I explicitly wrote down a proof that does not depend on how you regulate the K. No, it really doesn't.
So that's the point that you made?
Yes, it absolutely does not. You can go through, if you want to spend a really boring evening, I can tell you exactly what's wrong with each of their regulators, but none of them does what they. I mean, some of them are just mistakes. They say, use Carty calibrates twist operators as a definition, and you use a parity double, and just assume that the two parities are unentangled, but they're not. They're never unentangled, and you can see exactly where that breaks down. So any regulator you like, let's say in their parity double, again, you do this prescription, it defines a boundary state. But in the boundary state, the two parities are always actually not only not unentangled, they're maximally entangled. So no, none of their regulators is correct. They all have to be equal. because you can prove in a regulator-independent way that there just is no tensor factorization of the Hilbert space.
Simeon?
Yeah.
I mean, there are examples of conform field theories in 2 dimensions which do not have stress tensor. And in those cases, in particular, I would say that the answer that you would, I mean, what you would say is that you cannot.
What do you mean? Actually,
Long-range Ising model, for example.
The what?
Long-range Ising model.
Yeah, okay. I wouldn't call that a conformal. Yeah, okay. I'm really talking about local conformal field theories.
No, but even as you could say that it's a bad theory in some sense, that it does not have a local, but it certainly admits a lattice regulator.
But not a local lattice regulator.
Not a local one.
I mean, I'm assuming the bounded nearest neighbor property for all these lattice regulators. And by the way, you can even relax that. You can, have couplings between neighbors that fall off exponentially or something. Just you assume that they don't fall off power law. But I think the theory you're talking about, you do have to have power law. Power law is, power law falling off explicit couplings in the Hamiltonian.
So in this case, even having a lattice regulator will not give you a tensor factorization on the Hilbert space.
Yeah, that's right. Or maybe it does if they fall off with a fast enough power or something. But yeah, I really want to avoid theories like that because they're really weird.
And probably have followed the Nielsen, Neon theorem because we improve, we modify everything on the logic.
But none of these modifications is local in the sense that I'm talking about.
I just say the main is the same way as the lattice. We use lattice regulation to improve modify something.
Right, but all of those modifications violate some of the assumptions. So, for instance, domain-wall fermions, if the transverse space is compact, you actually have both chiralities and the gravitational anomalies not vanishing. If the transverse space is non-compact, then the spectrum on the circle is continuous. So, right, so I'm really assuming discrete spectrum on the circle, unitarity, all the nice. Oh, and slack fermions, by the way. I don't know if you know what those are. You know what those are. Slack fermions are exactly the kind of thing that you're talking about. They have in real space. So slack fermions is just something where in the Brouin zone, you have discontinuous jumps of the frequency as a function of the Bach parameter. But in real space, that corresponds exactly to power law, the suppressed couplings between sites arbitrarily far away.
It seems that the proof that you gave depended crucially on the Cardi condition for the boundary.
But the Cardi condition isn't assumed.
No, I'm not saying it's assumed. What I'm asking is, how can it possibly? How do you see a possible generalization to 6 dimensions, for example?
Oh, so the strategy for proving things about 6 dimensions isn't to try to reproduce the proof directly. Right? Maybe one can, but it's not a convenient way to do it. The strategy is to just use descent, dimensional oxidation. So, for instance, suppose you have. So there are actually 2 purely gravitational anomaly coefficients in 6 dimensions. The factorized one and the non-factorized one. So if the factorized one is non-zero, for instance, then if that was non-zero and you dimensionally reduce on a 4-manifold with non-vanishing signature class. Actually, I forget what the number of signature class. If the first term class is non-zero, there's some difference. I forgot. But one of those 2 or some combination, whatever.
You want the first punctuality to be non-zero.
Well, the first punctuality to be non-zero. Okay. Then you get a non-vanishing gravitational anomaly in 2 dimensions. So you know for sure that in 6 dimensions, if the factorized anomaly is non-vanishing, then there's no lattice regulator.
But there could exist spatial slicing which does not amount to spatial slicing in 2 dimensions.
No, just dimensionally reduce. Just take a product.
Yeah, but what I'm saying is that the tensor factorization that I would propose for the 6-dimension theory may not be compatible with that dimension reduction.
I think maybe I understand what you're saying, but I'm not sure.
I mean, if it goes like crisscrossing all the dimensions, how can you preserve that property under?
Okay, well let's forget for a second about tensor factorization. talk about lattice regulators. Suppose you had a lattice regulator for the 6D. If you had a lattice regulator for the 6D theory, then you could write it for whatever dimensional reduction you wanted, and you would get a contradiction. And you would think that, by the way, that should be obvious that there's no lattice regulator for the 6-dimensional theory, but actually there have been proposals for them, and I believe that this proof dispels any such possibilities. Although it doesn't kill a 7-dimensional gapped lattice theory with a 6-dimensional boundary. That's actually a viable construction.
But what's wrong with this type of?
Oh, it's exactly the same thing that went wrong with Jonathan's proposal for the 2-dimensional case. If you cut the 7-dimensional bulk, you don't create a boundary for the 6 dimensions. You just create another. You create 2 disconnected 6-dimensional boundaries.
This is basically so you're showing that you can't factorize the Hilbert space explicitly, which I need to understand a little bit.
Neither explicitly nor implicitly.
No, explicitly, whatever. Yeah. So, but I think that there's I mean, as you said, I mean, what one really wants is some generalization of a quantity that has certain properties of the entanglement entropy.
One certainly does want that, doesn't one?
Correct. And I think that as you said, the same problem occurs in gauge series, and people have ways to fix it.
No. It's a very different problem.
I understand it's a different problem. Yes, I understand. But just looking at these papers once again, it seems to me that they have the way they define it is by defining the mutual information of 2 regions, and that's something that's by taking the entangling surface, expanding it a little, defining the mutual information of regions, and that's well defined, and then taking that limit to 0. So they explicitly say, in fact, they don't want to use a lattice regulator.
I didn't assume a lattice regulator.
No,
That's why I spent all of this effort proving.
No, but the mutual information is more to get around the thing that he didn't want to talk about, which is the short distance stuff.
That's right.
Right.
So
That's not what he's talking about.
Right. It doesn't know the long distance stuff. There's even been there's been a claim actually in a paper which I haven't understood. There's actually been a claim that the gravitationally anomalous case, their definition violates strong subactivity. I can't verify or falsify that claim, but if you define it in one of these convoluted ways, none of which just to take an example, right? Their parity double proposal that really doesn't work at all, because the 2 parities are actually very strongly entangled with each other. So there's no way that you can assume that the density matrices you define in that way are going to satisfy any sort of inequalities. I think that there's no evidence that any of their proposals will satisfy the quantum information theoretic properties that they're supposed to have. And it's been claimed in some rather obscure paper that they don't. And my next agenda is to understand whether it's actually true or not. But again, it's really infrared then. It's not, it doesn't have to do with the regulator, because you can regulate, as I say, completely in terms of the normalized Hamiltonian and not worry about the UV out.
What does this say about holographic duals of theories with C left not equal to C right?
Good. Right. So all of these proposals came about trying to find something that would be the conformal field theoretic definition of a Ryutakiyanagi-like thing in the bulk, in a certain effective theory which has Einstein gravity and a gravitational Chern-Simons term and nothing else up to the Planck scale. I don't really want to speculate about it, but since you're begging me, twisting my okay. Ow, that hurts. Okay. I believe our best guess is that there are that really what these guys are showing is the UV incompletability of pure Einstein Chern-Simons theory in 3 dimensions. And by pure, I'm meaning it up to the Planck scale. So you know, the derivation or the proof, the justification of the Ryutakiyanagi formula, even in the non-anomalous case, doesn't work if there is a tower of states between some other scale and the Planck scale. For instance, if the dilaton is weak and there's a hierarchy between the string scale and the Planck scale, the Ryutake-Nagy formula is just wrong. It doesn't give you the right answer for weakly coupled Yang mills. It only gives you the answer for infinitely strongly coupled Yang mills. So our best guess, based on some casual perusing of the literature, talking to some people who work on these things, is that it's really a proof of UV incompletability. That if there's a gravitational Simon's term, that there are always states, a tower of states parametrically below the Planck scale. At least if it's a macroscopic gravitational anomaly. If C left minus C right is comparable to C12. And let me just give some intuition for why you would expect that to be true. So when there's a mismatch between the two central charges, typically there's a large chiral algebra on one side. But that means you have to expect that there are a lot of low-lying states that don't have any bulk interpretation. Right? It seems to be just inconsistent with the actual spectrum you would get of Einstein-Chern-Simon's gravity and bulk. So I don't know, but my best guess is that they're just that effective theory is just never realizable in the UV.
How would the non-factorization of the Hilbert space show up in the bulk theory?
Oh, so, well, good. I mean, you could compute correlators. So right. So the non-factorization, I guess, in that scenario where there's just a large chiral algebra making up the difference, the non-factorization would just be in the correlators of the pure chiral algebra part, and then it would just reduce to basically it would be like the chiral fermion case. Where even there we haven't, truly proved that there are no factorized states, but I think yeah.
Sorry, Simeon. Going back to this long-range case lattice model.
Yes.
What happens if I strip off half the points? What is the infrared fate of that?
See, then I think you can't assume that the bulk Hamiltonian flows to the same thing, right? Because it was strongly interacting with all the things you stripped away. So the bulk Hamiltonian itself might be different.
But it will flow to some conformal field theory, right? Wouldn't it?
I don't know what it would flow to. I mean, the Zimmer-Lojikov principle in the C theorem.
If this FK hypothesis and this Zimmer-Lojikov.
No, I'm just talking about we don't even know now that the bulk is going to flow to the same thing. It's not local enough to draw that conclusion. You can't apply.
Not necessarily the same thing, but some conformal field theory, not necessarily.
We can't even assume that. I mean, all the machinery that guarantees you that, which is basically the C theorem, all depends on having a local stress tensor, and you don't have that. So I don't know, but I think you can't. The stuff isn't there that guarantees you that